All right, welcome to physics. We're going to start a new unit today. We're finished with Newton's laws. We are moving on to energy. We're going to talk about energy conservation. And we generally start off talking about work before we get to that, okay? So we're going to do a quick review of things we know about work. We're going to add in a couple new things, a couple spicy things to get you thinking about the calculus of this a little bit. This is AP Physics C after all. Okay, so let's start with an equation here. We know that work is a force times a distance, F delta x, or you might see F delta r in your book. You might also see FD. Okay, another way we can think of this, and we're going to tack a cos theta on there as well. We'll talk about why. This is great. Last year we defined it as work equals FD parallel, okay, or you could put the parallel symbol right there. It means that the parallel component of the displacement is what we care about when we're calculating work. Okay, now work comes out in the unit joules, and it relates closely to energy. That's why we talk about it at the beginning of this unit. Work and energy go hand in hand. If I do work, I have the ability to change things about the energy. If I do work, sometimes I can increase or decrease kinetic energy. If we do work, we can change the potential energy of an object. So that's why it's important when talking about this. Okay? So a great example to start with, a lot of teachers start with this example, and it's really good. Okay, it helps us understand a lot of aspects of work. So let's say we're going to pull something. I'm going to choose, since it's winter in Colorado, let's say we got a kid here on a sled. I don't know why the kid is standing, probably because I'm not a good artist. Okay, but we got a kid standing on a sled, and then we've got older brother, sister, cousin, whatever, okay, pulling on the kid. So here's a rope. Okay, we've gotten a kid grabbing onto this rope, and we've got the force of tension, or we could call it a force applied, pulling on the kid. So I'm going to call this force of tension. All right, and we're going to start, before we get into the work stuff, we're going to start by just drawing an FVD. Okay, so here's the center of mass. We're going to have mg down, and we're going to have force normal up. I'm going to draw it smaller than mg, okay, because of this y component of tension. We know that from Newton's laws pretty well by now. Okay, over here we are going to have friction, okay, resisting our pulling force. Okay, now we're going to need to break up force of tension into x and y. So let's use a different color. Let's use dotted lines. We know we can't put components on AP FRQs, but we need these. Okay, we're going to put them on here. Okay, this is FTX. This is FTY. All right. Now, when thinking about work here, we need to talk about the work done by all of these forces and their components. And it's not hard. You're going to see right away that this is no big deal. Okay, but if we don't slow down and think about each force and the work it does, then we get ourselves into trouble. Okay, let's tack a theta on here. Okay, if the person wasn't pulling at an angle, if they were just pulling horizontally, this would be a little easier. Okay, angles make it slightly more tricky. All right, now this cos theta, this is the theta we're talking about. Okay, the angle between the force that we care about and the distance that we're going to go. So let's see. Let's get out a sparkly color of G2. Look at that. It's got a little glitter in it. I love these G2s. Okay, we're going to label a delta x on here. okay, or you could call it distance. Okay, both terms are kind of thrown around there in books and AP stuff and whatever. Okay. The angle between the force and the displacement. Now I could have drawn displacement right here. Okay, I might have made it a little bit easier, but it would clutter up my diagram. This theta matters. Okay, we want the cosine or the parallel component to the displacement. So we taught it like this last year. All right, cos theta we're going to throw in this here. And I taught you that as well in general physics. Okay, so what are we going to do with this? Let's talk about the work done by each and every force here. We'll go back to good old dark blue. Okay, so the work done by, we're going to start out with the force of tension here. Okay, and it's got two components. So first let's talk about work done by Ftx. All right, what we're going to do here is we're going to say force of tension, all right, in the x direction times the displacement. Okay, now if we're going to do that to calculate the force of tension in the x, that's going to be force of tension times the cosine of theta times our displacement. Okay, so here you see very quickly that we're using this equation. We're going to get the work done by the parallel component. Okay, and this is going to do some kind of positive work. Okay, positive joules are going to be done by that force. Okay, and if we look at what theta is, all right, theta right here, that gives us the parallel component to this, and so it's going to come out to positive work. All right, now work done by Fty. Okay, if we look at that, the cosine of theta, let's look at this. This is up, this is in this direction. They're at 90 degrees to each other, so the cosine of 90 is 0. And so we're going to get 0 joules of work done. Anytime you have a force that is perpendicular to the displacement, it will do zero joules of work. Okay, cosine of 90. And what that means is that force is not doing anything to cause this movement in this direction. Okay, force normal. Work done by Fn is equal to 0 joules. All right, it is perpendicular. The work done by force of gravity, or mg, is equal to 0 joules. Okay, now let's talk about friction. Work done by force of friction is equal to force of friction times delta x times cos theta. Okay, now if we knew the force of friction, we knew delta x, we could plug in numbers. We do know theta. So what we would do here is we would plug in 180 degrees. All right, cos 180 equals -1. Okay, you can plug it into your calculators to prove that to yourselves. So the force of friction is going to do negative work. All right. Let's put that. We're going to get negative work, which is going to be some negative amount of joules. Okay, now work is a scalar. It does not have a direction, okay? Pointed in that direction, that's really not the direction of the work, that's the direction of the force, okay? That does not mean, remember, scalars still can be negative and positive, they just don't have a direction. Okay, so if we add up all of these values, okay, what I'm saying is our positive joules done by FTX, our 0, our 0, our 0, and our negative joules, we would get the net work. Okay, and so I'm going to cross that out. I'm going to move that down. Work net is equal to the sum of all of these joules right here. Okay, and we could plug that in right here. And what we like to do with that is we like to set it equal to the change in kinetic energy. Okay, and so here's the rule. If the work is positive, if we get a positive net work, we get an increase in kinetic energy. If we get a negative net work, we get a decrease in kinetic energy. That means the thing is going to slow down. Okay, we can expand this a little bit. Work net is equal to delta KE, 1/2 mv final squared, okay, minus 1/2 mv initial squared, okay. That is our change in kinetic energy. We have KE final minus KE initial. Okay, change in kinetic energy. All right, now some things we're going to do with this. Okay, let's go back up here to where it says graphs. I'm going to draw a line here, and we're going to talk about some different situations where we're going to apply this. Okay, and what we just did was this. We took a constant force. Okay, we're not talking about friction right now, we're talking about this force. And if we graphed it, okay, F and delta X, the graph of that force would be like this. Okay, it's a constant force, it's not changing. Now the work done is the area beneath that graph. Okay, so we're going to shade this area in right here, and that is the work done. Okay, if I take a snapshot of this, okay, to see what the area means, I'm doing a force times the distance, which is work. Okay, now what we're going to do with this, let's put a definition up here that's going to be in your book and all over the place. Okay, work is equal to the integral of force with respect to displacement, F dx. All right, now some of you haven't got to integrals in calculus yet. That's okay. This is a good preview to what you're going to learn in your calculus class. This area right here, which we could calculate really easy without using calculus because it's just a rectangle, that's what an integral is. It's an area under a graph. Okay, and we've gone over that a little bit. We will get more into it. Okay, let's complicate it a little bit. What if we have a changing force? Here's the next hardest thing we can do with this. What if we have a force that's doing that? Okay, the most common example of that is a spring. So let's say over here we've got a spring, it's coiled like this, and we're going to exert a force in this direction to stretch that spring. Okay, so it is going to go some delta x. And the thing with springs is the force isn't constant. So as we apply this force, the spring will pull back harder and harder the more we stretch it. Okay, and that produces a changing force graph like this. Now, you may remember that the force of the spring, Fs equals kx. That is the equation of this line. Okay, let's check it out. We got y Let's write it. Y equals mx. This is a linear relationship. Okay, our y value, force of the spring. Slope is the k value, and x, we are graphing the change in x. So slope equals k. That's the spring constant. And what that does, if k is bigger, that means it's harder to stretch. Like if we were dealing with shock absorbers on cars, that's going to be in the thousands here. If we are dealing with the spring we did in lab last year, that little tiny stretchy spring, that's about 5 newtons per meter for the K value. Okay, now the work to stretch it is the area under this graph. Okay, this still applies right here. This area is super easy to calculate because it's just a triangle. Okay, you don't really need calculus for that. In addition, this area is equal to the stored potential. So potential energy is U, or PE. For spring, we put a S, and 1/2 kx squared. Okay, now it's also notable that this graph could be just some other changing force, like with our sled over here. Let's say the person increased their force as time went by and distance went by. It would still be this graph, and K would represent how many more newtons you are using per meter. Okay, it wouldn't be a spring constant per se. It would be the changing newtons per meter. All right, now where it gets a little bit more interesting here is if we have a force that is not changing in a linear fashion. Okay, let's say we have a force that's changing exponentially. Here's where we really need our calculus. Okay, the work done by that force is the integral of the force with respect to the displacement. Okay, here's delta x down here, and the area of this graph is, that's when we're going to need our calculus to get it. Okay, so we'll go over that in class. I just wanted you to have a basic understanding that all of these areas are work, okay, and different degrees of how we calculate them. All right, let's real quickly go over power. I know this video is getting a little bit long. This is going to be super quick. Okay, I needed a little more space. So down here are notes on power. Last year, you calculated your horsepower and your wattage. Okay, watts. All right, the definition of a watt. 1 watt, that's how we abbreviate it, is equal to 1 joule per second. Okay, so it's how quickly work is getting done. All right, and our equation tells us that power is equal to work over time. Okay, so it involves the time component. And we can say work is F delta x, or FD. I'm going to leave out the cos theta for this part, and we're going to divide by time. Okay, now here's a sneaky physics ninja move that is maybe a little bit new. Okay, delta x over t. That looks suspiciously like something we know. And it's velocity. So a force times a velocity is also a way to get power. Okay, another way to look at it, and I think this is maybe how it looks on your equations page, change in kinetic energy over time. Okay, so we'll come back to this. We'll apply some problems to all of this, and hopefully this is a good review slash introduction of some new stuff for you. Okay, thanks for watching.